So rumor has it you may need to know how to do thin films. They're fairly straightforward, but they've got a little twist. So let's assume that we have a film of some kind, and let's say it's got an index of refraction of n, and it's just floating in a region of air, right? So it's got an index of, we'll say 1. The way it works is that light will come in, and there's some portion that we know is reflected, so that'll be ray 1. And then some portion is transmitted, and it'll really refract and do other stuff in here. But we're going to make the assumption that this angle is pretty close to 0. It's almost a straight shot. That way we don't have to deal with triangles, right? And figuring out, well, by Snell's law, how far does it travel? So we're going to make this assumption. Some of it goes through. It does this reflection business again. And then here we have 2 rays that are now meeting up, and they're going off to an observer. Depending on how far apart these 2 waves are from each other, there could be interference. So what we need to consider is what is the total phase shift between these 2 in order to give us, just whatever the shift is. Is it constructive or destructive? So a question that we should ask, if we want constructive, we know that we need integer numbers of wavelength shifts, right? Need integers. And you might be tempted to say, oh, well, then the path length is, what's the path length? If this is the width, we'll call it L. This ray just bounces off directly. The second ray is how far apart? Well, that's 2L, right? So you might be tempted to say 2L, or not 2L, the path length is 2L. And if you want integers, you might be tempted to say, oh, well, we'll just make it equal to that. There's a problem in this analysis. You need integers overall. But there are other things that are at work. When you have a reflection off a surface, it's possible for there to be a phase shift. So this is not necessarily always true. What is always true is that you need integers overall. So what are some rules? If the reflection is from low n to high n, then you do get shifted by half a wavelength. The wave reflects backwards or upside down. We've done these experiments before in piano wires, right? From lower mass densities to higher, the reflections are different depending on where you start and where you end. If you go from something high to low, then there's no shift. So a better way for us to do this, like the cookbook will always succeed method. Let's redo this same problem. This is 1, this is n, this is 1. First thing we want to know is, what do you want? If you want constructive, great. For the sake of argument, let's say that we do. What do we need? If we want constructive, we need full integers. Okay. Next question, what do you have? And that means check the reflections. So based on this, I'll do just kind of what we said before. I'll look at the first ray. I come in from 1, and then I bounce off n that we say is higher than 1. That's a low to high interaction. So this ray is phase shifted by a factor of a wavelength of 2. How about the bottom one? The bottom one comes in. It's n. It bounces off this lighter or less dense surface. So it bounces back without a phase shift. And we don't see any phase shifts from transmission, only from reflection. So this ray is 0. Compare the 2 of these and ask yourself, how far apart are they? What do we have? Check the reflections. I have a wavelength over 2 shift already between these 2. So here's the question of, what do you want to do for the path length? What path length will give you what you want? We want full integers. Here, we have a half. We need the path length difference to contain another half such that it'll cancel this one out and give us the full integers we need for fully constructive interference. So I'm going to choose a path length that isn't just the, m. I'm going to choose m plus 1/2. Okay? And the purpose of this is to make sure I wrap an extra half into the path length to add to this one to make sure everything comes out to a clean, even integer, if the goal is constructive interference. What is the path length? Assuming that we're coming in fairly normally and without, strange angles, it's a reasonable approximation to say if this is some thickness L, the second ray, when it splits off from the first one, goes L down plus another L back up, right? So the path length difference here would be 2 times the thickness. I did something else that was a little bit strange here. I didn't just call this the wavelength, I called it lambda n. So that's the wavelength inside this material. Remember, inside the glass or oil or whatever, light slows down. That means that with the same frequency but less speed, it covers less distance. So the wavelength inside an index of refraction is the vacuum wavelength divided by n. And that's just something that we need to take into consideration also. So this seems counterintuitive. If you want to solve any problems related to thin film interference, in this case, our equation looks like m plus 1/2 lambda over n. And this looks weird. Yeah, I say it's counterintuitive because we were finding constructive interference. But in this case, we use the path length difference equation that has a half. It looks weird, but it does make perfect sense if we look at the bigger picture, right? Constructive needs whole integers. Well, not all of the action is happening here. Some of it was happening up there. Redo the problem and let's make it a little bit different. Let's say I've got a layer of some kind of weird gunk. I want to say benzene, but I don't know what its index is. So let's just say that we have something like, I don't know, some heavy oil or something with a 1.5 index on the bottom. Floating on top of it, I guess we'll make water. And then above all that is air. We've got a problem that we have yet to figure out. Is it constructive or destructive? So who cares? Check the reflections right away. That's the first thing you should be doing, right? So here I go from 1 to 1.3. That's lower off of higher. There's a shift. I got 1.3 off 1.5. That's lower and higher. That's also a shift. So questions. If you want constructive, what do we need? You need full integers. We have no shift already, right? Both of them are shifted the same amount, so they're both the same. They're still in sync. So we have no shift. And what do we want? Keep it. Keep no shift. Don't introduce any more halves. Maintain this already in sync, situation that we have. So I might use 2L equals, in this case, m lambda n, where this is n is 1.3, because that's where the material is doing the interference. Okay, if we want a destructive, you need halves. You have none. So what do you want? Halves. I need something to give me that half to split everything out, make it destructive. So I would use that form of the equation. Okay, so it's kind of hard to make a cookbook. I could make a matrix with like 4 different possible cases or even more, depending on, well, did the top shift or the bottom shift? I don't know. If this was the constructive case, and let's say in this case where you already had a half due to reflections, let's say that we want a destructive instead. Okay, that's what you want. You need halves. I've got halves. So what do I want? Don't screw them up. Okay, so if we want to not screw them up, we would want to use an equation that looks like this, right? You've already got the shift that you want due to the reflections. Don't mess it up. Maintain that and use a path length that introduces only full integers. So I hope this was helpful in getting us through the thin films. Cases that this might be useful is questions of like, you know, what wavelengths would fully interfere, or what's the thinnest coating that you would have to put on something to make destructive interference at a particular wavelength, right? And this is a good question for something like the anti-glare coating on glasses, right? We'll see if we can detect mine. I don't know if it'll show up, but you should be able to see kind of greenish purplish colors in that glare. If I didn't get the AR coating on it, that would look bright white. So what's going on? There's a very thin layer of a thin film that selectively tries to interfere out a lot of the visible wavelengths that, you know, I would see. And you can't get all of them, right? We've got red, green, and blue. So we have to just kind of pick the brightest one and try to target it. So to do that, you might be asked, well, find all possible L's, right? And make a table. And you would do that by finding the path length. Okay, here's the solution for L. And then saying, well, if M equals 0, that's the smallest case. If M equals 1, that's a little bigger, 2 is bigger, 3 is bigger, and so on. So typically the question is like, what's the thinnest layer that you can put in just for economics, right? So that's a type of question you might see.